The topic we've been studying is often called electromagnetism, or just E&M for short. But at this point, we've really just been looking at the magnetism part. It's not clear so far what electricity or electric charges have to do with magnetism, if anything. So it turns out that when electric charges move, they create magnetic fields. I want to be clear about this. An electric charge by itself sitting there will create an electric field. We already know about that, but it won't create a magnetic field. However, as soon as it starts to move, it now creates a magnetic field in addition to that electric field it already had. So we're going to look at some situations where we have electric charges moving and therefore creating magnetic fields. Now, one of the simplest ways to get an electric charge moving is to make an electric circuit where we have wires with current running through them. When current flows through a wire or through any conductor, any piece of metal, a magnetic field will be created around that wire. Now, we can figure out the exact shape and direction of that magnetic field by using what's called the first right-hand rule. So, imagine we have a wire or a long conductor, kind of like this rod shown here. And we've got electric current flow, it suddenly starts to flow through it. We want to figure out, so the electric current is illustrated by this red arrow here, I for electric current. There's current flowing up through this rod. Now, current is moving charge, and moving charge creates a magnetic field. We want to figure out, using this rule, what that magnetic field that's created by the current looks like. So the first thing to know about the right-hand rule is you use your right hand. Seems obvious at this point, but often there's a point, kind of a few days into this topic where people are so used to using the right hand rule, they forget the most important thing about it, and that's that you need to use your right hand. People will by accident start to use their left hand. Not going to give you the right answer. So, take your right hand, point your thumb in the direction the current is flowing. So we see that's what's happening in this diagram here. The current is flowing up through the wire, and this person has pointed their thumb in that direction. Next step is wrap your fingers around the wire to make a fist. That's what's going on over here. Wrapping fingers around the wire to make a fist. Now look at your fingers. Your fingers are pointing, at this point, in the direction of the magnetic field created by the current. So you can see, in this case, the fingers are sort of wrapping around the back of the wire and then coming to the front and then going around the front of the wire. Well, that's exactly what the magnetic field is going to look like. The magnetic field is going to look like loops drawn down here and down here. Remember, magnetic field lines always form complete loops. They don't start and end at certain places like electric field lines do. And these loops are going to be going the same direction around the wire that your fingers are. So that shows us how to find out what the magnetic field created by a current, electric current, looks like. Another thing to note about this magnetic field, and this is particularly obvious if you look at sort of this diagram down here. When we're close to the wire, these magnetic field lines are very close together. They're tightly spaced, meaning the magnetic field is strong. But when we're a bit further away from the wire, the magnetic field lines are more spaced apart, meaning the magnetic field is getting weaker as we go further away from the wire. So let's try and apply this rule ourselves a little bit by looking at these diagrams down here. So here I've drawn a number of different wires, and they're going to have current flowing through them. And then I've got these large circles here, 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 and these ones over here. And these large circles represent compasses. And we know that a compass always points in the direction of the magnetic field. So we're going to use our right hand to figure out the direction the magnetic field is going in, and then draw which way the compasses would point. Again, knowing the compasses will point in the direction of the magnetic field. So let's look at these first wires over here on the left. In this wire, I've got sort of a positive charge or a positive terminal of a power supply up there and a negative terminal down here. So through this long wire, I'm going to get current flowing. And we know that current flows from positive to negative. So I'm going to draw my current flowing like this, and I'll label that I. And the same is going to be happening in this other wire. And in these second two wires, my terminals, my positive and negative, are switched, so current's going to flow the other way, again from positive to negative. Okay, so then around each of these wires, I've placed a compass that's going to indicate which direction the magnetic field is going. And we're going to try and figure that out ourselves. So in this first one, let's apply the right-hand rule from up here. If you take your thumb of your right hand and you point it in the direction this current is going, so point it going down the page, and then pretend you're grabbing that wire with the rest of your fingers. You'll find your fingers are sort of going into the page on the left side of the wire, and then they're curling around and they're going to the right behind the wire. And then if you keep curling them around, they would sort of come up out of the page on the right side of the wire. And on the part of the wire sort of in front of the wire, between you and the wire, your fingers are going to the left. So they're sort of doing this circle around the wire where in front of the wire, between you and the wire, they're going to the left, and behind the wire, they're going to the right. So, since this compass here is in front of the wire, it will point the direction the magnetic field is going in front of the wire, which we said was to the left. Now the second compass, again, the wires in this case has current going the same direction, but this compass you'll see is behind the wire. So again, if we apply our right-hand rule, our thumb is going down in the direction of the current, then we pretend to grab the wire with our fingers, making a fist, and we note that our fingers behind the wire are pointing to the right. So this compass that's behind the wire is going to point to the right in the direction the magnetic field is going, back there. Now in these next two examples, we've switched the current direction. So here we're going to again point our thumb going up the page. Pretend we're going to grab that wire with the fingers of our right hand, making a fist. And in front of the wire, between us and the wire, where this compass is, we see our fingers are going to the right. And they curl around the wire so that behind the wire, our fingers are going to the left. Okay, now something we haven't really had to deal with much so far, that we're going to have to deal with today, is a problem where we've got arrows going in basically 3 different dimensions. Most of the physics problems we've done so far, things are going maybe left, right, and up, down at the same time, or northeast or north, south, and east, west at the same time. When we get into electromagnetism, we're going to have one problem where some things are going up, down, Some things are going left, right, and some things are going into and out of the page. So 3 different dimensions all at the same time. Now, it's easy to draw arrows that are going left, right. It's easy to draw arrows that are going up, down. It's harder to draw arrows that are going into and out of the page. So the way we do that is by introducing a couple of new simple symbols. So an X is the symbol we use to represent an arrow going into the page. And a dot is the symbol we use to represent an arrow coming out of the page. If it helps you to remember this, think of an actual physical arrow, like the kind that's fired from a bow and arrow. And imagine that arrow is fired away from you. It's going into the page. The part of the arrow that you would see, sort of leaving you, is the back of the arrow, which has fins on it, looking kind of like an X. Now, conversely, imagine instead that an arrow is fired from a bow directly at you, and it's coming towards you. It's coming out of the page. The part of the arrow that's closest to you, the part of the arrow that you would see, is the tip, the point on the front of the arrow as it comes out of the page. And that point will look like a dot. So, when you see a dot, think of the point of an arrow coming out of the page at you. When you see an X, think of the fins of an arrow going into the page away from you. So that shows kind of what's happening in these next 2 examples over here. Here, we have a circular wire, and it's got current in it, but that current is going into the page. So, yeah, this X represents our I, our current, and it's going into the page. So, I'm going to take my right hand, and I'm going to put my thumb in the direction of the current. Orient your right hand so your thumb is sort of right over top of this wire, and your thumb is going into the page. Then make a fist with your fingers, and you'll see that your fingers are kind of wrapping around that wire in a clockwise manner. That means the magnetic field around this wire will be going in clockwise loops, like this. Now, we actually aren't being asked to draw the whole magnetic field, but by drawing that, we can kind of see which direction these compasses will point. Compasses point in the direction of the magnetic field, so this guy will be pointing like that, and here, and here, and here. Okay, let's look at this last example. Down here, there's my wire. My wire is going into and out of the page. And that dot in the middle represents the current. Dot looks like the point of an arrow coming out at me, so I have current coming out of the page. So I want to know what the magnetic field created by that current looks like. I take my right hand. I put my sort of the heel of my hand where that arrow is, and I make sure my thumb is coming out of the page, just like that dot. Then I wrap my fingers to make a fist, and I see my fingers are going in a counterclockwise direction. So the magnetic field created by this current is going to be going like this. Again, it'll be strong, close into the wire, and it'll be weaker, more spaced apart field lines as I get further away from the wire. So you can see now where these 4 compasses are. They're going to point in a direction that matches the magnetic field. So they're going to be pointing like this. So now we can kind of look back at all of these compasses we drew and all of the currents. And there's something sort of important we can note. The compass always points parallel to the magnetic field. And more than that, it points in the direction of the magnetic field. Also note that the compasses are always pointing perpendicular to the current that caused that field. So when an electric current causes a magnetic field, those two things, the field it causes is perpendicular to the current. All right, so let's move on. So that kind of shows us how a current carrying wire can give us a magnetic field. And the neat thing about this magnetic field is it can easily be turned on or off. Because when we have current flowing in a wire in an electric circuit, it's easy to turn that electric circuit on or off by disconnecting the battery or using a switch. It's easy to turn electricity on or off. So this is kind of new. This is something we couldn't do with a permanent magnet, like a bar magnet. You can't really turn them off easily. Now we have a magnetic field we can turn off, but this still leaves something to be desired. This new magnetic field we've created around these wires, it turns out it's not particularly strong. It also doesn't have north and south poles in an obvious way. So we can't use it conveniently to like push and pull on other magnets at our will like we could with those bar magnets, those permanent magnets. And it's also very non-uniform. Remember, it was really strong, close by the wire, and it was really weak further away from the wire, and it's always going a different direction. It's always curving, always changing direction. There's no sort of region here where the magnetic field looks like it's going the same direction for a period of time. It's very non-uniform. Turns out that it would be great if it was strong. It would be great if it had north and south poles, and it would be great if it was uniform. So there's some shortcomings with this magnetic field that we've created around a wire, even if we can turn it on and off. However, we can fix all these shortcomings by taking that wire and wrapping it around into a spiral or a coil, kind of like we see down here. The result, this wire or coil we can create, is called a solenoid, or we can also call it an electromagnet. And we're going to look now at how that works. So we've taken a long piece of wire and we've wrapped it like this into a coil. Ignore for a while these blue magnetic field lines that are around this. Just look at the coil. Now, to kind of show what's going on here, I'm going to imagine we've taken that coil and imagine we have sort of like a saw. Think of the saw blade as running like this. And we're going to take that saw. Let's see if I can do this here. And we're going to use the saw, right? Cut up and down. We're going to cut through this solenoid from left to right. So I've basically split it in half. And once I've split it in half, I basically have a cross section where I can now look, at the inside of each of these wires. And that's what we're doing over here. This is sort of my cross section of this solenoid. You can see there are sort of 5 points on the bottom where I'll have cut through the wire, and that's what I'm looking at down here. And then there's 4 points on the top where I've cut through the wire, and that's what I'm looking at up here. Now we're going to use our X's and dots again to show the direction the current is going. So let's say my current kind of comes in from my electric circuit on the bottom left here. So here's where current goes into my wire and into my solenoid. And we're going to have this current go into the page. Now that current heads into the wire here. It loops around, and when it gets to the top here, it's now coming out of the page. And then it continues to loop around in front of us, and then when it gets to the bottom, it's now going into the page again. And we can keep going through this, and it comes out of the page at the top and goes into the page at the bottom. Out of the page at the top, into the page at the bottom. Out of the page at the top, into the page at the bottom. So all those X's and dots represent the direction my current is going. Now we're going to look at these one at a time and think about the magnetic field each little piece of wire here would create using the right-hand rule. So let's start by looking at this one down here. Take the thumb of your right hand. This current is going into the page, so point your thumb sort of down at your paper, going into the paper. And then you see that your fingers will want to wrap around in a clockwise manner. So we're going to have magnetic fields going clockwise around this piece of wire. Okay. And then the same is going to be true of the wire beside it. It's also got current going into the page. So the field created by it will be going clockwise. Now let's look at those bits of wire on the top. They all have dots in them. So if you take your right hand and you place it over one of these pieces of wire so that the thumb is coming out of the page, like these dots represent, you'll notice that your fingers then tend to curl counterclockwise around these pieces of wire. So along each of these, the magnetic field is going to be trying to go counterclockwise. It will be going counterclockwise. Okay, so each of these little segments of wire by itself will create a magnetic field. But what's really powerful about this solenoid or this electromagnet is the way these electric fields add together. So let's look at that. First, let's look in between all these little bits of wire. In all of these places, I've got one wire creating an upward magnetic field and one wire creating a downward magnetic field. What that means is going to happen is all of those magnetic fields will cancel out. So we can see it's just going to start looking like that. And the same thing is going to be true on the top. These guys are going to cancel. These guys are going to cancel. So it's going to start, if I draw it properly, it's going to start looking like that. Now let's look at what's happening actually inside the solenoid. Here, I've got the magnetic field created by these guys on the top, and they're all going to the right. And I've got the magnetic field created by the wires at the bottom, and they're also all going to the right. So here, instead of canceling, I've got 9 pieces of wire, all of which are trying to create a magnetic field going to the right. So in the middle of this solenoid, all of these little magnetic field contributions add together to give me a very strong magnetic field that is very definitely going to the right. And that's kind of what we see over here in this sort of finished diagram. In between the loops and sort of on the outside, I've got a pretty weak magnetic field because magnetic fields are sort of canceling out or they're far away from the wires. But inside that solenoid, these lines are very tightly spaced, meaning the magnetic field is very strong and they're all going directly to the right. So if you look at this sort of finished drawing of what the magnetic field through a solenoid would look like, if we sort of drew all of our arrows and kind of added them all together, we'd get a picture like this. We notice a few things. So one is that just as with a bar magnet, a solenoid also has north and south poles. Recall that on the outside of a magnet, the field lines go from north to south. So over here, we kind of see the field lines leaving this end and coming towards this end, meaning this is going to be our north pole, and this is going to be our south pole. On the outside of the magnet, the field lines go from north to south. On the inside of the magnet, they're going from south to north. Now, this is true for regular permanent magnets, like bar magnets too, only we don't often talk about the field inside the magnet because it's hard to go inside there. It's just solid metal. In a solenoid, though, the inside is hollow, so we can very easily go inside there and put things in there, and they'll experience this strong magnetic field. Also note that outside the solenoid, the magnetic field is, as I mentioned before, weak. Yeah, and we can tell that because these lines are very spaced apart, and it's non-uniform. Right? Over here it's going to the left. Over here it's, there it's going to the right. Over here it's going to the left. Over here it's kind of wavy. Can't really decide which direction it's going in. That's outside the solenoid. However, inside the solenoid, we see the magnetic field is strong and uniform. I mentioned this already, but these magnetic field lines in here are very tightly spaced, meaning it's strong, and they're all going one direction, to the right. So we've sort of, by constructing the solenoid, we've fixed some of the problems we had with just the plain wire by itself. The plain wire made a field that wasn't particularly strong. In a solenoid, it is. The plain wire didn't have north and south poles. The solenoid does. The plain wire gave a field that wasn't very uniform. Inside the solenoid, we have a field that is very uniform. And to top it all off, just like the plain wire, because this magnetic field is created by an electric current, we can turn it on and off at will. We've created a powerful, uniform magnetic field with obvious north and south poles that we can turn on and off whenever we want. So the next thing we might want to know, since we might use this to actually attract some magnetic objects, how strong exactly is this field on the inside? One of the benefits we said is that it is strong. How strong is it? And the next thing I'm going to present you with is a formula for calculating that. And the formula looks like this. B is the symbol we use for the magnetic field strength. There's the Greek letter mu with a subscript 0 after it. But we pronounce this 0 like we're British. We don't call it 0, we call it naught. Like N-A-U-G-H-T. So this is called mu naught. And it's a constant. Just like big G is always 6.67 times 10 to the negative 11. And just like Coulomb's constant, K, is always 9 times 10 to the 9. Mu naught is one of those constants. Big G sort of tells us how strong gravity is in our universe. K sort of tells us how strong electric forces are in our universe. Mu naught sort of tells us how strong magnetic fields are in our universe. And the other things that go into this formula are N, which is the number of loops in my coil when making my solenoid, and L, which is the length of the solenoid, and I, which is the current going through the solenoid. So let's write all this down. Mu naught has a special name. It's a pretty cool name. I like it. It's called the permeability of free space. And again, I think of it as just how strong magnetic fields are in our universe. And just like big G is always the same number and Coulomb's constant is always the same number, mu naught is always the same number, and that number is 4 pi times 10 to the negative 7. Capital N, as I said, is the number of loops in my coil or my spiral. L is the length of the solenoid. By length of solenoid, this is worth sort of mentioning. I mean sort of from here to here. If you took a measuring tape or a ruler from between those two green lines, that would be the length of your solenoid. It's not the total length of all the wire that was used to create the solenoid. It's not that. It's not the, how far it is from one sort of side of the solenoid to the other, or the diameter of the solenoid. It's not that. It's the length of the actual finished solenoid from here to here. That's an important thing to realize. So length of the solenoid, not the length of the wire. And then I, as I said, is the current flowing through that wire. Now these guys will all have units. Electric current is measured in amps. Length is measured in meters. Number of loops, that's just going to be a number, because we'll count that. Magnetic field strength is kind of a fun one. It's a bit different from our other fields. So gravitational fields were in newtons per kilogram. Electric fields were in newtons per coulomb. Magnetic field is just measured in Teslas, or capital T for short. And that means that mu naught, our permeability of free space, can be written as Tesla meters per amp. Now, we're going to use this equation in 1 second, but I want to just let you know that there's another form of it. It turns out that the actual number of loops we have in total in our solenoid doesn't necessarily matter. And the actual length of the solenoid in total doesn't necessarily actually matter. As long as I know the ratio of these two, I can find the magnetic field. So for example, if I know that there are 2,000 loops per every meter, then it doesn't actually matter how long my solenoid is, whether it's 1 meter or 1,000 meters. If I know that how tightly wound it is 2,000 loops per meter, then I can just plug that in for N and L at the same time. So we can write that in the form of another formula, mu naught lowercase n I, where lowercase n is the number of loops per meter, or how tightly wound the solenoid is. So depending on kind of what information we're given in the problem, we'll either use this version of the formula or this one. So with that said, let's try and just use this to really quickly calculate the strength of a magnetic field inside a solenoid. So here we have 126 meters of wire. So I've got a bunch of wire all straight. It's 126 meters long, and I take it and I coil it up to make a solenoid that's 25 centimeters long and 4 centimeters in diameter and has 1,000 loops. Then I hook it up to an electric circuit and I make 9 amps of current flow through it. And I'm asking you, what is the strength of the magnetic field inside? Well, the formula we just have is for the strength of the magnetic field inside a solenoid. So let's use that. Okay, so first of all, I'm going to put in mu naught. Then I'm going to put in N, the number of loops, which is 1,000. Then I'm going to put in L, the length of the solenoid. Now I have a bunch of things that are sort of distances here. I've got the total length of wire that I started with. Then after it's coiled up, I have an actual coil, a solenoid, and it's got this as its diameter and this as its length. Well, the number here that's relevant is this middle one, the length of the finished solenoid. Remember, it's not the diameter from here to here. It's not the total length of all the wire that we use to make it. It's simply the length from the start to the end of the finished solenoid. And in this case, that's 25 centimeters. And then we need the current flowing through it, which is 9 amps. Plugging that in, we get 0.0452 Teslas. And I encourage you to try and actually get this number on your calculator yourself right now. It can be a bit tricky. In particular, typing mu naught into your calculator can be tough. A lot of calculators will give you an error if you try and type it in exactly as it is. The issue here is they don't like you taking an irrational number, pi, and then putting it to the power of something, putting pi sort of into mixing it with scientific notation. Calculators often don't like that. So one thing that you can do to kind of get around this is you can kind of use some brackets, sort of calculate 4 pi first, get an answer, and then multiply that answer by 10 to the minus 7. The other thing you can do is kind of reverse this. Do 10 to the minus 7 first, and then multiply it by 4 pi. Try that with your calculator now. Make sure you can get through this calculation without getting an error and getting this final answer. All right, so to sort of recap, we learned that magnetic fields and electric charges are actually very closely intertwined. Whenever an electric charge moves, it creates a magnetic field. And we can figure out the shape and direction of that magnetic field by using what's called the right-hand rule. And that showed us what the magnetic field looks like around a single wire that's carrying current. Then we said, what if we take that wire and we wind it up into a coil shape? Well, then we get something called a solenoid. And it has a lot of benefits. It has a strong, uniform magnetic field on the inside. It has a north and south pole. And we're able to turn this magnetic field on and off by turning the current on and off. We can use the right-hand rule to sort of figure out exactly the direction that the magnetic field is going at each point, sort of inside a solenoid. And we can use this formula down here to find the strength of the field inside the solenoid. So that's sort of the gist of today's lesson, looking at wires carrying current and solenoids carrying current, and figuring out what direction the created magnetic field will be, and also what its magnitude is.